Welcome dear learners. We are continuing the course Quantum Chemistry. In this module, we are discussing eigenvalue and expectation value postulates of quantum mechanics. The major contents of this module are eigenvalues and eigenfunctions, eigenvalue postulate of quantum mechanics, then expectation value postulate, illustration of expectation value postulate, postulate of time dependent Schrodinger wave equation, and the postulates of quantum mechanics, a final consolidation. First of all, eigenvalues and eigenfunctions. The word eigen is a German word which means own or characteristic. When an operator operates on a function, produces a constant times of the function is called an eigenfunction. The resulting constant value is called eigenvalue. That is, when an operator operates on a function and the result of the operation is the function back multiplied by a constant, then the function is called eigenfunction of the operator and the constant value is called eigenvalue. This can be illustrated by considering this example. Here d by dx operates on e raised to 2x and the result is 2 into e raised to 2x. That is, we get the e raised to 2x function back multiplied by a constant 2. Therefore, as per this equation, it is clear that e raised to 2x is an eigenfunction of the operator d by dx and 2 is the eigenvalue in this equation. Now, we can take several examples to find out eigenvalues and eigenfunctions and to check which of the following are eigenfunctions of some operator, etc. For instance, in this problem, we are going to find out the eigenfunctions of the operator d by dx. That means we are going to find out which of these functions are eigenfunctions of the operator d by dx. We know that d by dx is a differential operator. Therefore, we have to perform first order differentiation with respect to each and every function and we will get the result. On analysis of the result, we can conclude that which of these are eigenfunctions of d by dx. We can proceed by one. First of all, we are going to discuss sin x. We have to check whether it is an eigenfunction of d by dx or not. It should be noted that d by dx of sin x, you know the differential of sin x is equal to cos x. That is 1 into cos x. Or the result of this operation is a new function. I should not get the function back multiplied by a constant. Therefore, it is clear that sin x is not an eigenfunction of the operator d by dx. Now we can take the second function e raised to 2x. d by dx of e raised to 2x. Differential of e raised to x is equal to e raised to x and e raised to 2x is 2 into e raised to 2x. That means on differentiating e raised to 2x, d by dx of e raised to 2x is equal to 2 into e raised to 2x. That is, I got e raised to 2x back multiplied by 2. That is, e raised to 2x is an eigenfunction of the operator d by dx with the eigenvalue 2. Now we can take 2x. That is the third problem. That is d by dx of 2x. It is clear that this is equal to 2. Here also the function is not retrieved. That is 2x is a function which is not an eigenvalue of the operator d by dx. We can take e raised to minus I for x as another example. d by dx of e raised to minus I for x. the result is equal to e raised to minus I for x into minus 4i. That is, I got the function back multiplied with the minus 4i. That is, we are multiplying with a constant term. That means the function e raised to minus I for x is an eigenfunction of d by dx with eigenvalue equal to minus 4i. And the last function, that is cos 2x, it should be noted that d by dx of cos 2x, that is equal to minus sin 2x into 2. Here also, I should not get the function back. That means cos 2x is also not an eigenfunction of d by dx. In a consolidation, among these 5 examples, 5 functions, e raised to 2x and e raised to minus I for x are the eigenfunctions of the operator d by dx. Now we can continue the above problem with another operator. We can try a new operator, that is the second order differential operator, that is d square by dx square. And we are going to assess which of these functions are eigenfunctions of the operator d square by dx square. First of all, we can check sin x, that is d square by dx square of sin x. That means we have to differentiate sin x twice. D by dx of sin x is equal to cos x, and we have to perform one more differentiation, that is equal to minus sin x. The final result is minus sin x. That is, performing twice the differentiation leads to the final result, minus sin x. That is equal to minus 1 into sin x. This implies that the function sin x is an eigenfunction of the operator d square by dx square with eigenvalue equal to minus 1. Now we can take the case of e raised to 2x. D square by dx square of e raised to 2x. That is, we have to differentiate e raised to 2x twice. First of all, d by dx of e raised to 2x. That is equal to 2 into e raised to 2x. I have to differentiate it once again to get to the second order differential. Therefore, again I am differentiating e raised to 2 into e raised to 2x by with respect to x. That is 2 into e raised to 2x. The result is 4 into e raised to 2x. 4 into e raised to 2x. Thus it is clear that I got e raised to 2x back multiplied by a constant 4. Thus the function e raised to 2x is an eigenfunction of the operator d square by dx square. Now we can check whether 2x is an eigenfunction. We know that the first differential of 2x is equal to 2 and the second differential of 2x is equal to 0. Therefore, the function 2x is not an eigenfunction of the operator d square by dx square. The fourth function, we can take the fourth function. We have to differentiate it twice. One first differentiation, that is d by dx of e raised to minus I for x. The result is minus 4i into e raised to 4x. I have to perform one more differentiation. So, the e raised to I for x, e raised to minus I for x. So, the final result is e raised to minus I for x into minus 4i into minus 4i. That is 16i square. I square is equal to minus 1. So, the final result is 16 e raised to minus I for x. This will be the final result of differentiation of e raised to minus I for x twice with respect to x-axis, or d square by dx square of e raised to minus I for x is 16 e raised to minus I for x. Hence, it is also clear that e raised to minus I for x is an eigenfunction of the operator d square by dx square. We can move on to the last, that is cos 2x. On differentiating cos 2x, we are getting minus sin 2x first. On further differentiation, we are getting cos x. Yes, the final result, that is d square by dx square of cos 2x can be proceeded like this. On first differentiation, the result is minus 2 sin 2x, 2 sin 2x. On further differentiation, I will get minus 2 into cos 2x into 2. That is minus 4 sin 2, minus 4 cos 2x. Minus 4 cos 2x is the final result. Minus 4 cos 2x is the final result. Thus it is clear that in the last case also, I got the function back multiplied by a constant. That constant is minus 4. The final result is minus cos 2x into 4 or minus 4 cos 2x. Thus, in the last problem, the eigenvalue is equal to minus 4. Thus, it is clear that the function cos 2x is an eigenfunction of the operator d square by dx square. Thus, it is clear that among the 5 problems given, except third one, that is 2x, all others are eigenfunctions of the operator d square by dx square. Thus, we familiarized the concept of eigenvalues and eigenfunctions. Now, we can move on to the postulate, the eigenvalue postulate. The eigenvalue postulate is one of the important postulates of the quantum mechanics, and the statement of the eigenvalue postulate is like this: the allowed value of an observable are eigenvalues ai in the eigenvalue equation a hat psi I is equal to ai psi I. It should be noted that here in this expression, capital A represents the physical quantity or the observable. We already learned that for every observable, there is a corresponding linear Hermitian operator in quantum mechanics. So, A is the observable and A hat is the corresponding linear Hermitian operator that represents capital A. Suppose if A is potential energy, then A hat is the potential energy operator. If A is momentum, then A hat is the momentum operator. Like that. A is the property, A hat is the linear Hermitian operator corresponding to that property. Then allowed values of the property A are small ai, and that values are eigenvalues which satisfies this equation. And here in this equation, psi I represents the wave function. So, to get allowed value of an observable, we have to operate the wave function with the operator corresponding to the observable, and we have to get the function psi I back multiplied with some constant, and that constant value is the eigenvalue which are allowed values of the observable capital A. In a very simplest way, it can be said that the allowed values are eigenvalues. Now, the Schrodinger wave equation is an eigenvalue equation. We can prove that, we can show that the Schrodinger wave equation is an eigenvalue equation. We know the time independent Schrodinger wave equation is Hamiltonian psi equal to energy into psi. Here, H hat is an operator called Hamiltonian operator. Hamiltonian operator. Hamiltonian operator is the total energy operator. That we already learned that H hat is equal to minus S cross square by 2m del square plus V. The first part represents kinetic energy and the second part represents the potential energy. So H hat or Hamiltonian operator is the total energy operator. From this equation, it is clear that this mentioned Schrodinger wave equation is an eigenvalue equation. How is like that? Hamiltonian operator operates on the wave function of the system psi, and the result of the operation is the wave function back multiplied by this constant. The constant value or the eigenvalue is energy. Thus, we can say that the Schrodinger wave equation is an eigenvalue equation with eigenvalue equal to energy of the system. That is, Schrodinger wave equation is obtained by operating wave function with the Hamiltonian operator, and the result of the operation is wave function back multiplied with energy. So, Schrodinger wave equation is an eigenvalue equation with eigenvalue equal to energy of the system under consideration. Now, we can move on to next postulate called expectation value postulate of quantum mechanics. Expectation value is otherwise called average value. A is an observable. A can have average values. Whenever we are measuring A, if we are getting so many values, then we have to take its average. So the average of the observable, average value of the observable is represented as A average. And how to calculate A average? A average can be calculated based on expectation value or average value postulate. I already mentioned that average value is otherwise called the expectation value. The average value or expectation value of an observable A is obtained from this mathematical relation. A average or expectation value of A is equal to integral limit of integration from minus infinity to plus infinity. If the integral limit is not shown, it is implied that the limit of integral is from minus infinity to plus infinity. Here the integral limit is shown. So A average is equal to integral minus infinity to plus infinity psi star A hat psi d tau. What are the parameters present in this equation? D tau represents dx into dy into dz to give an implication that this integral mentioned here is a volume integral or a triple integral. And psi is the state function of the system under our consideration. We already mentioned the fact that psi star is the complex conjugate. How we are getting the complex conjugate? In order to get to the complex conjugate of a wave function, write down the wave function first and replace the terms I with minus I. Then we are getting complex conjugate. If there is no imaginary number or I in the wave function, then the function is said to be a real function and psi will be equal to psi star. So psi star is the complex conjugate of the wave function psi, and A average can be calculated as integral minus infinity to plus infinity psi star A hat psi d tau. Then what A hat represents? A is the property. We are measuring average value of the property A or the observable A. In the postulate of quantum mechanics, we already learned the fact that to every observable, there corresponds a linear Hermitian operator. So, we are discussing with the property capital A. So, there is an associated linear Hermitian operator. The linear Hermitian operator associated with A is designated as A hat. So, if we are dealing with the momentum, then property A is momentum and A hat will be the momentum operator. And the momentum of which system we are considering? The wave function of that system is psi. Psi star is its complex conjugate. So, by utilizing this expression, we can find out the average value of an observable. This equation is very important and we can do several practices for finding out average value of different kind of observable in certain circumstances. Now, illustration of the expectation value postulate or average value postulate. The problem is like this. Find out the average value of x. X is simply position along x direction. Of a particle in 1D box problem, this problem we will consider more detail later. Particle in 1D box with edge length is equal to small a and with infinite height. The wave function for the system is mentioned here. The wave function of the system is psi n equal to root of 2 by a sin n pi by a into x. By using the expectation value or average value postulate, it is possible to find out the average value of the position. By using this expression, x average is equal to integral 0 to a psi n x raised to n psi n x raised to n psi n dx. Here, I simply ignored the star, that is psi star n is not mentioned. The reason is that the wave function is already given. In the wave function, there is no imaginary part. So, the wave function is a real function. So, we can say that psi n is equal to psi star n. So, by utilizing this expression, it is possible to find out the expectation value or average value of position x for a particle in 1D box. And we can proceed mathematically according to this expression. And x, average value of x is equal to integral limit is from 0 to a because the particle in 1D box is here the limit is 0 to a and psi n, the value of psi n is root of 2 by a sin n pi by a into x multiplied by x hat. X hat is simply multiply with x into another psi n root of 2 by a sin n pi by a into x. D2 is not required, so the last term is dx. On simplification of that integral, on evaluation of that integral, we will get the average value of position of particle in 1D box. We can proceed some more. X average equal to, here you can see root of 2 by a, that is a constant term. That 2 by a can be taken outside the integral side, integral 0 to a, sin n by a into sin n by a, that is sin square n pi by a into x dx. We have to integrate this equation by adopting product rule of integration, and sin square theta is equal to 1 minus cos 2 theta by 2. By taking necessary steps for simplification, we can finally reach at the expectation value or average value of position in particle in 1D box problem. On further solution, we are getting the final value as, and we can make some replacement, sin square theta that is equal to 1 minus cos 2 theta by 2. Sin square n by a into x is equal to, can be replaced as 1 minus cos 2 n pi by a x by 2. That 2 can again be taken outside the integral sign, and we can proceed with the further mathematical simplification steps to get the final value x average. That is average value of position of a particle in 1D box equal to a by 2. This you can test by using paper and pencil, and you can do the simplification steps systematically, and the final result will be average value of x is equal to a by 2. Thus, it can be concluded that the average value of position x of a particle, that particle as such is placed along the x-axis with edge length is equal to a. That's why the integral limit is from 0 to a, and the average value can be calculated as equal to x average is equal to a by 2. A is the edge length, so a by 2 is the exact half of the edge length, and a by 2 is the average value of position of particle in 1D box. Now we can move on to another illustration, another problem. based on expectation value postulate. Here we have to find out average value of momentum for a particle in only box with edge length same as above, that is small a, and height is infinite. The wave function for the present system is again similar, that is psi n is equal to root of 2 by a into sin n pi by a into x. And we can proceed as above. First of all, the average value postulate. A average is given by integral minus infinity to plus infinity psi star a hat psi d tau. For the present problem, a hat, that is momentum operator, a hat is equal to px hat, that is equal to minus ih cross dou by dou x, we already learned. And psi n and psi star n both are same, and the value is equal to root of 2 by a into sin n pi by a into x. d2 is not required since we are having only one variable. Therefore, d2 is replaced by dx. And the integral limit is from minus infinity to plus infinity, just changed to 0 to a, because for particle in only box problem, the limit of integration is from 0 to a. Therefore, a average should be replaced by px average. Px average, average value of momentum of a particle in only box, can be calculated by the equation integral 0 to a psi star same as psi, that is root of 2 by a sin n pi by a into x. Psi star is over, then a hat is this minus ih cross dou by dou x, minus ih cross dou by dou x into psi is again root of 2 by a sin n pi by a into x dx. On evaluation of this integral, we will get the average value of momentum. We can do some more simplification. Root of 2 by a, root of 2 by a is a constant and it can be taken outside the integral sign as 2 by a. 2 by a, here you can see a minus ih cross. So, minus ih cross is also taken outside, and dou by dou x can be changed to d by dx. Therefore, this expression will be sin n pi by a into x, 0 to a, integral 0 to a, this is px average. Px average is equal to minus ih cross 2 by a, integral 0 to a, sin n pi by a into x into dou by dou x. Dou by dou x can be marked as d by dx since we are having only one variable. D by dx of sin n pi by a into x dx. Sin n pi by a into x dx. Px average equal to 2 by a into minus ih cross integral 0 to a sin n pi by a into x, differential of sin n pi, cos n pi by a into x into n pi by a into n pi by a. Sin x, cos x, n pi by a is again a constant, can be taken outside, into dx. On further substitution and taking constant outside the sign, we will get the final average value of momentum of particle in only box problem. And on solving this, you can prove that the final value, the average value of the system is equal to 0. That means Px average is equal to 0. Thus, it can be concluded that the average value of momentum of a particle in only box with edge length small a equal to 0. This is another important observation. So, in the previous problem, for the particle in only box, the average value of position is a by 2. And here it is proved that the average value of momentum is 0. And we can do one more problem that is associated with calculation of energy. Calculate the average value of energy for a particle of mass m confined in only box with edge length small a and infinite height. The wave function for the system is again same. Sin is equal to root to 2 by a into sin n pi by a into x. How we can proceed to this? First of all, we have to find out average value of energy. Average value of energy of the system. So we have to get the energy operator first. It should be noted that total energy operator is the Hamiltonian operator, and Hamiltonian operator is minus s cross square by 2m del square minus s cross square by 2m del square plus v. And for a particle in only box problem, inside the box the particle can never be at rest. That means the potential energy part vanishes. Therefore, the energy operator will be minus s cross square by 2m. Del square is for a 3D box. Dou square by dou a square plus dou square by dou y square plus dou square by dou z square. Here the particle is moving along x direction. Hence, the wave function contains a component of x only. Therefore, the energy operator expression contains no del square. Instead of which, only d square by dx square is present. So, this is the energy operator of the present system. That is, E hat is equal to minus s cross square by 2m into d square by dx square. So, we got energy operator. We know about psi n and psi star n both are same, that is equal to root of 2 by a into sin n by a into x. So, we already got energy operator and wave function. The limit of integration is also known, that is from 0 to a. Therefore, the average value of energy can be calculated like this. Integral 0 to a psi star n, that is simply psi n, root of 2 by a sin n pi by a into x into energy operator, that is minus s cross square by 2m d square by dx square into again psi n, that is root of 2 by a into sin n pi by a into x. The last element is dx. Minus s cross square by 2m, 2 by a can also be taken outside the integral sign. Therefore, the result is minus s cross square by 2m, minus s cross square by 2m into 2 by a. This is the average value or expectation value of energy. Minus s cross square by 2m into 2 by a into integral 0 to a sin n pi by a into x into d square by dx square of sin n pi by a into dx. Sin x on differentiation gives a cos n pi by a divided by n pi by a. Again, you can also do one more integration and further substitution to get the final value of energy average. It should be noted that on simplification of this integral, we will get a final average value of energy associated with the system. The final energy value associated with the system E average will be same as energy of the particle in only box problem. What is the expression for energy of the particle in only box problem? That is equal to n square h square divided by 8ma square. Here a is the edge length, m is the mass of the particle, n is the quantum number, h is Max Planck's constant. Therefore, E average is equal to n square h square divided by 8ma square. This is the average value of energy for a particle of mass m confined in an only box with edge length and infinite height. The average value is the same as energy of the particle in 1D box as given by energy equal to n square h square divided by 8m a square. A is the edge length, m is the mass of the body, h is Planck's constant and n is the quantum number. That all about the illustration of expectation value postulate. Thus, we have find out 3 parameters, 3 average values associated with the particle in 1D box problem. First of all, we covered the average value of position, that we got it as a by 2. Then we evaluated the average value of momentum, that we got as 0. And finally, we elucidated the average value of energy associated with the system, that is equal to the energy expression, which is same as energy average equal to n square h square divided by 8m a square. Now, postulate of time dependent Schrodinger wave equation. This is the last postulate associated with the quantum mechanics, and this postulate deals with the state function and its connection with the time dependent Schrodinger wave equation. It should be noted that the wave function psi of rt is a solution of, is an acceptable solution of time dependent Schrodinger wave equation. This is time dependent Schrodinger wave equation. Is cross dou psi by dou x or dou psi of xt by dou x equal to minus s cross square by 2m del square plus vrt into psi of rt. Ih cross dou psi by dou x equal to minus s cross square by 2m del square plus vrt into psi of rt. For convenience, here x is, here we put x represents the coordinate. So as a generalized form, we can represent it like this: Ih cross dou by dou x or dou by dou r of psi of rt, dou by dou r of psi of rt, that is equal to minus s cross square by 2m del square plus vrt into psi of rt. This term is nothing but the Hamiltonian operator, Hamiltonian psi of rt, and this is time dependent Schrodinger wave equation. It should be noted that the wave function psi of rt is an acceptable solution of time dependent Schrodinger wave equation. Thus, we studied various postulates of quantum mechanics. Throughout the discussion under the course quantum chemistry, we have studied 5 important postulates of quantum mechanics. Now we can have a consolidation of all the postulates. First of all, the state function postulate, which is simply the state of a quantum mechanical system can be completely described by a function psi of rt that depends on coordinate of the particle and on time. Now the second postulate, that is the operator postulate. A physically observable quantity can be represented by a linear Hermitian operator, and to get this, write the classical mechanical expression first and replace the terms px, py and pz respectively by minus is cross dou by dou x, minus is cross dou by dou y and minus ih cross dou by dou z respectively. Next is allowed value postulate or eigenvalue postulate, which states that the allowed values of an observable are eigenvalues. Next one, the average value or expectation value postulate. The average value can be calculated by using the expression A average is equal to integral psi star a hat psi d tau. And the last postulate, that is the time dependent Schrodinger wave equation postulate. The wave function psi of rt is a solution of time dependent Schrodinger wave equation. Thus, we have discussed all the postulates of quantum mechanics so far. That's all about this module. Thank you.